This is Pre-Calculus A, Unit 5, Exponential, Logarithmic, and Piecewise Functions, Lesson 4, Logarithm Rules in Solving Logarithmic Equations. This lesson is fairly long. It's got at least 4 different kinds of questions or problems that it demonstrates. All of them use what we call the rules of logarithms, or logarithmic rules. So here are the rules that we need to know. And I'm not going to take the time to derive them, because to do so would take way more time than we have. But they're all related to the rules of exponents. So you recall that if you have 4 to the third times 4 to the second, that's 4 to the 3 plus 2, or 4 to the fifth. So multiplication turns into addition. The corresponding logarithmic rule for that is this. The sum of logs, log of A plus log of B, is the same as the log of a product, log A times B. Same with the difference. Log of A minus log of B is the log of a quotient, log of A divided by B. Okay? Then there's the power rule, and this is a really powerful one. This is a really important one to remember. The log of A to the x, or A to the n, is n log A. That is, you can take an exponent on the argument and move it down in front. Or you can take a multiplier, a scalar in the front, a factor, and move it to the exponent position. Okay? So that's really important here. And we're going to use that quite a bit. So these are generally the two rules that are used, and they can be used forward and backward. We can turn a product into a sum. We can turn a sum into a product, and vice versa. Okay. The real power of the exponent one is it allows me to turn an exponential function into a linear function, and that's really powerful here. All right, so let's use it. There, as I said, are a number of kinds of questions you might be asked to do. In one, you're asked to combine, to take something that's expanded and simplify it. So let's demonstrate that. I'll demonstrate that with this example here. I'm going to simplify or condense 4 log base 5, and I'm going to leave the base off. Well, I guess I'll put it there just for the sake of simplifying. But log base 5, because the base really doesn't matter in this particular case, just that the bases do need to agree, equals 3 log 5 of x plus 2. The first rule I'm going to apply is the exponent rule. A number in front can be moved to the position of exponent. A number in front of a log can be moved to the position of exponent. So this becomes log base 5 of x to the 4th minus log base 5 of x plus 1 equals log base 5 of x plus 2 to the 5th power, or to the 3rd power. Okay? Now I'm going to use the quotient rule. So the difference of logs is the log of a quotient. Difference of logs is a log of a quotient. So log base 5 of x to the 4th over x plus 1. So we take the quotient of the arguments, equals log base 5, oops, that was supposed to be minus, not equals. I was like, wait a minute, I'm solving an equation. That's not what I meant to do. That was supposed to be minus. Miscopy. All right, so we're just simplifying. Minus, minus, okay? All right, so minus log base 5 of x plus 2 to the 3rd. Okay, now we have another difference of logs, right? A difference of logs is a log of a quotient. So log base 5 of. Now I'm going to combine this. To divide a fraction means to multiply by the denominator. So this is in the denominator x plus 1 times x plus 2 cubed. And on the numerator we've got x to the 4th. So we have simplified. We've taken a logarithm that's been broken apart and condensed it into a single logarithm, okay, using these rules. Another thing you'll want to be able to do is go the other direction. You'll want to be able to expand a logarithm. Okay, so let's do that. So here we go. Let's expand the logarithm. Let's do this one here. The natural log. Ln is just natural log base e. E is just a number, 2.718282, of cube root of x over y. Now here, this does take a little bit of knowledge of rational exponents. Okay? Rational exponents. So we want to expand this. So this is x to xy. Cube root is xy to the 1/3. That's a fractional exponent. So I'm going to use the power rule for logarithms. Log of a power is a power times a log. Okay, so this is 1/3 ln x over y. And now I'm going to use the quotient rule. The log of a quotient is the difference of logs. So 1/3 ln x minus ln y. Now I can distribute the 1/3, or I can just leave it like this. And I'm going to leave it like this because it doesn't simplify it to distribute. Okay, so that's expanding it out. Okay, we can solve logarithmic equations, and so I've got a couple of examples of these equations using logs. So here's one. The log, and when I don't put the base, the base is 10. So log base 10 of x plus log base 10 of x minus 21 equals 2. And I'm going to combine these, so I'm going to say a sum of logs is the log of a product. Log of x times x minus 21. Okay, and I'm going to distribute, so log of x squared minus 21x equals 2. Okay, now I'm going to write the base here because I'm going to use that to rewrite this as an exponential equation. Okay, remember the answer to a log is always an exponent. So 10 to the power of 2 equals x squared minus 21x. That's how we turn it into an exponential equation. The base, 10 to the power of 2, equals the argument of the log x squared minus 21x. Okay, and 10 squared is just 100. Subtract 100 from both sides. X squared minus 21x minus 100 equals 0. Factor. Factors of 100, whose difference is 21, are going to be 25 and 4. We need negative 21, so negative 25. So x equals negative 4 or 25. Now, one of the things we have to be aware of is you can't take the log of a negative number. So you need to check and see if the domain restrictions are broken. If I let x equal negative 4, the log of negative 4 is undefined. And so it can't be negative 4. And so we've got to make sure when we plug it in that it works. So log of 25 works. Log of 25 minus 21 is log of 4, and log of 4 works. Okay, so 25 is the only one that results in no domain restriction violations. Okay, so do remember that extra step at the end to check for extraneous solutions. Okay, here's another one, another kind of problem here. I've got two more problems here to do. Okay, let's go blue here. All right, so the natural log of 2 minus the natural log of x plus 3 equals the natural log of x minus the natural log of x plus 28. Now the strategy I used on the last one was to get it down to a single logarithm and then write it as an exponential function. In this case, I'm going to get it in the form of a log equals a log. Okay, and then I'll demonstrate what to do in that case. All right, So the log of a difference of logs is a log of a quotient. So the natural log of 2 divided by x plus 3 equals the difference of logs is a log of a quotient, the natural log of x divided by x plus 28. Okay. Now we happen to know logarithm is 1 to 1. The function looks like this, right? It's got an asymptote, a vertical asymptote. It passes the horizontal line test. It passes the vertical line test. What that tells me is the only way for two logarithms to be equal is for their arguments to be equal. Okay, there is no other way about it. So because of that, because logarithms are 1 to 1, we can write this equation: 2 over x plus 3 equals x over x plus 28. Okay, cross multiply. X squared plus 3x equals 2x plus 56. Get everything to one side. X squared plus 1x minus 56 equals 0. Factors of 56, whose difference is 1, are going to be 7 and 8, plus 8 minus 7. So x equals negative 8 or positive 7. Go back and check. Does negative 8 produce a violation? Negative 8 plus 3 is negative 5. Natural log of negative 5 is undefined. Can't use negative 8. 7 plus 3 is 10. That's positive. 7 is positive. 7 plus 28 is positive. So 7 works. By the way, it is possible for there to be no solution. So don't just assume because one didn't work that the other one will. It's not a given. Sometimes there's no solution to the equation. Okay, that's another strategy. And then you've got this kind of problem where you have nested logarithms of different bases. Okay, so let's do that here. Log base 81 of log base x of 64 equals 1/4. Okay, and I like the Ukrainian Russian dolls, nested dolls. Think of working from the outside in. Okay, let's rewrite this outside log base 81, as an exponential. So 81 to the power of 1/4 is log base 60 or log base x of 64. 81 to the power of 1/4 equals log base x of 64. That's just rewriting as an exponential. Now 81 to the 1/4 is the 4th root of 81. So what number to the 4th power is 81? Well, 3 times 3 times 3 times 3 is 9 times 9, or 81. So the 4th root is 3. So 3 equals log base x of 64. Now rewrite this as an exponential. So the base to the 3rd equals 64. So x to the 3rd equals 64. So x is the cube root of 64. What number times itself again is 64? I believe that's 4. 4 times 4 is 16. 16 times 4 is 64. Now check to see if this makes sense, or if this results in a violation. There's no violation to say log base 4 of 64. Log base 4 of 64 is 3. Log base 81 of 3 is 1/4. All right. So there we have it.